In 1941, a 23-year-old nobody walked into a seminar room at Princeton University and faced an audience that could have made any physicist on Earth lose his nerve. Albert Einstein was sitting in the front row, Wolfgang Pauli right beside him, John von Neumann, Eugene Wigner, the most terrifying collection of minds ever assembled in a single room. And this kid, who had never given a professional talk in his life, stood up at the chalkboard and started writing equations about particles that move backward through time. That kid was me. What happened in that room, and in the years that followed, put me on one side of a disagreement with Einstein that he carried to his grave. It wasn't personal. Einstein was one of the warmest, most generous men I ever encountered, but we disagreed about something fundamental, something about what reality is, about what nature actually does when you're not watching. And for decades, almost everybody assumed Einstein was right and I was wrong. It took until 1982, 27 years after he died, for someone to build an experiment that settled it. So what was the disagreement? And why did it take so long to resolve? That's the puzzle. Let me back up and set the scene properly. My advisor at Princeton was John Archibald Wheeler, one of the most imaginative physicists who ever lived. Wheeler and I had cooked up a wild theory about electrodynamics, about how charged particles interact with each other. The standard picture said there's an electromagnetic field floating around in space, and particles push on the field and the field pushes on other particles. We said, what if you throw the field away entirely? What if particles act on each other directly, across space and time, including backward through time? That's what I was presenting to Einstein, and afterward he came up and said something polite. He was interested. He and Pauli even got into a little argument with each other during the question period, which took the heat off me. But I noticed something in Einstein's reaction. He was willing to entertain unusual ideas about electrodynamics. What he was not willing to entertain, not then, not ever, was a particular implication lurking underneath it all. See, 6 years before that seminar, in 1935, Einstein had published a paper with two colleagues, Boris Podolsky and Nathan Rosen. People call it the EPR paper, and it laid out the most elegant argument Einstein ever made against quantum mechanics. The argument goes like this. Take two particles and let them interact, then pull them apart. Send one to Paris and the other to Tokyo. According to quantum mechanics, these two particles are still connected. They're entangled. Erwin Schrödinger actually invented that word the same year. Measure something about the particle in Paris, say its spin, pointing up or down, and instantly the particle in Tokyo has a definite spin too, not after some signal travels between them. Instantly, no delay. Einstein thought this was absurd. He called it spooky action at a distance. And his logic was airtight, given his assumptions. Either the particles had definite properties all along, like answers sealed inside envelopes before anyone opens them, or information was somehow leaping across the universe faster than light. Since nothing can travel faster than light, the particles must have carried their answers from the start. Quantum mechanics, which says the answers don't exist until you look, must be missing something. There must be hidden variables, some deeper layer of reality that quantum mechanics fails to capture. For a long time, this seemed like a philosophical argument. You couldn't test it. Whether the particles carried hidden answers or not, the predictions of quantum mechanics came out the same, so most physicists shrugged and moved on. Interesting question. Can't settle it. Let's calculate something useful. But I couldn't shrug, and the reason I couldn't shrug came from my own work. After the war, in the late 1940s, I developed something called the path integral formulation of quantum mechanics. It's a completely different way of thinking about how particles get from one place to another. In the classical picture, Einstein's picture, a particle goes from point A to point B along a single path. You calculate the forces, you figure out the trajectory, that's where it goes. Clean, definite, sensible. In my picture, the particle takes every path, every single one. It goes straight from A to B. It also loops around the moon. It zigzags through the rings of Saturn. It does a figure 8 around your head, every conceivable route simultaneously. Each path carries a little arrow, a phase, a number you can compute. When you add up the arrows from all the paths, the wild ones cancel each other out, and the reasonable-looking path is what survives the cancellation. I need you to feel the strangeness of this. I'm not describing a mathematical trick. I'm describing what nature does. The alternatives are real. The interference between paths shows up in experiments. You can measure it. It's as concrete as a rock. and this demolishes Einstein's position. Einstein said particles have definite properties. A particle is at a definite place, moving at a definite speed. My formulation says a particle is doing everything, everywhere, all at once. The definite-looking world you experience is what's left over after an unimaginable quantity of possibilities cancel against each other. The properties aren't sitting there waiting to be discovered. They crystallize out of the cancellation. The measurement is what creates the result. That was the core of what separated me from Einstein. Not a single dramatic confrontation, not a shouting match, just two ways of thinking about reality that cannot both be true. Einstein said the moon is there whether or not you look at it. My physics said something far more unsettling, that asking whether the moon is there when nobody looks is not even a well-defined question. You can only talk about what happens when you do look. The trouble was nobody could design an experiment to tell us who was right. Both sides made the same predictions for every experiment anyone could think of. Hidden variables or no hidden variables, the numbers came out identical. The debate seemed permanently stuck in philosophy. And in physics, if you can't test it, you learn to live without an answer. Some people made peace with that ambiguity. I never did, because the path integral wasn't ambiguous at all. It was screaming something very specific about reality. It just couldn't prove it in a way that would silence the other side. Then, in 1964, a quiet Irishman named John Bell, working at CERN in Geneva, did something brilliant. Bell was a careful thinker. He didn't publish often, but when he did, it mattered. He asked a simple question. If Einstein is right and particles carry hidden variables, definite answers sealed in those envelopes, then is there a mathematical limit on how correlated the measurements at Paris and Tokyo can be? The answer was yes. He derived an inequality, a ceiling. If hidden variables exist, the correlations between the two measurements can never exceed a certain number. It's a hard boundary, no wiggle room. But then Bell calculated what quantum mechanics predicts, and quantum mechanics blows right past that ceiling. The correlations are stronger than any hidden variable theory allows. If you could run the experiment, you'd know. Either the correlations stay below Bell's limit and Einstein wins, or they exceed it and the quantum picture, my picture, is how nature actually works. For 18 years, this sat on paper. 18 years. A clean, testable prediction that could resolve one of the deepest questions in all of physics, and nobody ran the experiment properly. Some people didn't believe it mattered. Others didn't think you could do it without loopholes ruining the result. Bell himself worried about the practical difficulties. Then came Alain Aspect. Aspect was a French physicist working at the Institut d'Optique near Paris. Young, determined, and very clever about experimental design. He proposed his experiment in 1975 and spent years building it. His setup used pairs of photons, particles of light, emitted from calcium atoms. The two photons fly off in opposite directions. At each end, a device measures the photon's polarization, which is like the direction its electric field wiggles. What made Aspect's experiment special, what made it different from the handful of earlier attempts, was a trick that went straight to the heart of the loophole problem. He set up optical switches that could redirect each photon to one of two different polarizers, and these switches flipped so fast, about every 10 nanoseconds, that the decision about which measurement to perform on each photon was made while the photons were already in flight. No signal, traveling at the speed of light or anything slower, could possibly get from one detector to the other in time to influence the result. The two measurements were completely independent. Whatever correlation showed up had to be genuine. In 1982, the results came in. Think about what was at stake. If the correlation stayed below Bell's limit, Einstein would be vindicated from beyond the grave. Hidden variables would be real. Quantum mechanics would be revealed as an incomplete approximation of something deeper and more sensible. The universe would turn out to be the well-behaved, deterministic place Einstein had always insisted it was. My path integral, with its every path at once madness, would be reduced to a clever calculation tool with no claim on reality. The correlations exceeded Bell's limit by 5 standard deviations. Not a marginal whisper, a clear, unmistakable violation. Einstein's hidden variables were ruled out. Nature does not carry sealed envelopes. The entanglement is real. The properties genuinely do not exist until measurement creates them. Spooky action at a distance is not a quirk of the mathematics. It is a fact about the universe. I want to be fair to Einstein because I always want to be fair. This result doesn't mean everything he believed was wrong. His general theory of relativity is one of the most magnificent constructions in the history of human thought. His work on the photoelectric effect helped start quantum mechanics in the first place. The man had physical intuition that bordered on supernatural, but on this particular question, whether reality is definite independent of observation, he was mistaken. And the path integral, this strange, every path at once way of thinking, was pointing in the right direction the whole time. There's a subtlety I want you to catch because people often miss it. Spooky action at a distance does not let you send a message faster than light. You cannot use entanglement as a telephone. When you measure the photon in Paris, what you get looks completely random. Flip a coin. It could go either way. The person in Tokyo also gets random results. It's only when you bring the two lists of results together and compare them side by side that the pattern appears, and the pattern is stronger than hidden variables allow. Nature is non-local, but nature is careful. She hides the non-locality inside the randomness so that no signal actually travels faster than light. The speed limit holds, but the correlations violate every classical expectation. After aspect, the floodgates opened. Other groups repeated the experiment with better equipment, closing more loopholes. By the late 1980s, the violation of Bell's inequality had been confirmed with enormous statistical certainty, up to 100 standard deviations in some setups. The quantum world is not classical. It does not secretly carry definite properties behind the scenes. And yet, something remains that we do not understand. We know the correlations are there. The math describes them perfectly. The path integral handles them. Quantum field theory handles them. Every prediction matches every experiment to extraordinary precision. But the question of what is actually happening, what sort of reality produces this behavior, that is still open. How are two particles, separated by any distance you like, coordinated so perfectly without any signal passing between them? The equations tell us the answer. The equations do not tell us why. I find that thrilling, not frustrating, because it means we are not done. Nature still has secrets, and they are deep ones, not technical puzzles, fundamental mysteries about the fabric of reality itself. Einstein wanted the universe to be reasonable on its own terms, without anyone needing to look at it. I understand that desire, it's a good instinct, but nature does not answer to our preferences. She does what she does, and our job is to find out what that is, not to argue about what it ought to be. I said something along those lines to Einstein once in a hallway at the Institute for Advanced Study, in much clumsier words than that. He listened. He smiled. He did not agree. The warning, if that's what you want to call it, was simply this. Do not fall in love with how you think the world should behave. Fall in love with how it does behave. And if the answer turns out to be strange, if particles really do take every path, if properties really don't exist until measured, if entangled particles really are connected across the cosmos in ways that make no classical sense, then accept it, test it, push it, but accept it. The greatest physicist of the 20th century could not bring himself to accept it. And it took the rest of us 40 years and some beautiful, painstaking experiments to prove that nature is wilder than he was willing to imagine. So let me leave you with this. If you could sit down with Einstein today, knowing what we now know about entanglement and Bell's theorem and the experiments that followed, what would you tell him? I think about that sometimes. I think he would have been disappointed. But I also think, underneath the disappointment, he would have been fascinated. Because more than anything, more than his theories, more than his reputation, Einstein loved nature. He just had trouble admitting that nature doesn't love us back in the way we'd like.